So I will present, thank you, Chairman. I will present a qualification of a metallic components produced by additive manufacturing for a space application. In particular, the space application was the Space Rider body flap assembly. So first, a few words about Space Rider. What is Space Rider? Space Rider is a space transportation system which will be used by Europe in the next year to access and to return from the low orbit. And the novelty of the program is that this, the vehicle will be used, will be reused, so will be used at least 6 times. It will be launched by Vega at sea, and during its mission, some experiments will be performed for technology demonstration. And after its mission, it will return on the Earth, and the payload will be recovered, and the vehicle will be prepared for the next mission. So the program is funded mainly by Italian governments with the collaboration of a European Space Agency, and more than 20 companies are involved in the project. So in the framework of the Space Rider project, CIRA, which is my company, the Italian Research Center, is in charge of designing, manufacturing, and qualification of the whole body flap assembly, which is this component here. And we have proposed an hybrid approach, an hybrid design. We use CMC for the control surface and metallic materials for the attachment to the cold structure, the orange components. Okay, so in particular, we have proposed to use T64 titanium alloy for the metallic components, and we have proposed to produce these metallic components by using additive manufacturing due to the complex shapes of the parts. So actually are 2 items, the inner flap and the outer flap, with the outer is the external one and the inner is the internal. We have used a standard from ESA for the qualification process. So this standard is for powder bed fusion additive manufacturing process for metallic materials and space application. And basically, there are 3 phases during the qualification: the definition phase, the verification phase, and the production. In the definition phase, hardware requirements are reviewed and compared with additive manufacturing constraints in order to define a preliminary manufacturing concept review. Then there is the verification phase. You can see here a lot of acronyms, but the principle is very simple. Basically, the aim of the verification phase is to verify the end-to-end manufacturing process through 2 testing campaigns, one at the sample level here and one at the prototype level. So the idea is to start from preliminary additive manufacturing procedure at sample level. Sorry, it doesn't work. However, the idea is to convert preliminary additive manufacturing procedure in verified additive manufacturing procedure through 2 testing campaigns. One at the sample level, which is the additive manufacturing verification plane, and one at prototype level, which is the prototype verification plane, PVP in the acronym. When the verification phase is concluded, is verified, then the production can be started. In the definition phase, we have chosen to use the electron beam technology as additive manufacturing technology. At CIRA, we have an Arkham A2X machine. So the main check was was about the dimension. We have checked if the dimension of the items fit inside the building envelope of the machine. And this was okay for both, for the inner and for the outer, of course. For the verification phase, as I mentioned before, we have followed this building block approach, starting from powder passing from specimen level, and finally concluding with tests at component level. Starting from powder, okay, this is a very important step because it is very important to define acceptable powder properties because the quality of the powder, of course, affects the quality of the final product. So acceptable powder properties were defined according to the test shown in the table, in particular in terms of chemical composition, particle size distribution, porosity, density, flowability, and morphology. Then we have moving to the simple level verification phase here. Okay. We have performed an extensive test, material test campaign. This is just a summary. Maybe for more detail, you can read the relative publication here, or just ask me. And this phase was very important in order to evaluate intrinsic material properties of T64 produced by IBM. And these results were used to define acceptance criteria, which were established in this phase. So we moved to prototype level test campaign. We have produced two prototypes, one for the inner flap and one other one for the outer flap, in two separate jobs. In each jobs, we have produced not only the prototype, but also some specimen, which we can call validation specimen, because I use it to measure some properties like density, tensile properties, or chemical properties. And so these properties are compared with acceptable properties in order to validate the job. The job was validated through testing, and some tests were performed on prototypes. First, we have performed some CT scan analysis on prototypes. No defects were detected, only residual powder was found in the internal zone of the prototype, because it is very hard to reach this zone with our cleaning system. We have performed also some static test campaign. The aim was to validate the numerical model used for to design the body flap assembly, but also to evaluate the capability of the body flap assembly to sustain the static aerodynamic loads during the re-entry phase. So this is the test article. In orange, you can see the additive manufacturing parts. And the test article was mounted on a suitable text fixture here. And we have used a balloon here, which was put between a flat plate and the test article here. And the balloon was connected to a compressed air source in order to simulate the aerodynamic loads. So the test was instrumented with the displacement transducer here, and here, and some strain gauges. Here you can see, for example, the displacement in these 2 points as a function of balloon pressure. As main results of this test was that no anomaly and no structural failures occurred during the test. The test was repeated 6 times in order to prove reusability of the test article on the same test article, of course. So the data were mostly consistent, repeatable, and well correlated with the numerical models. We have performed also some dynamic tests on the same test article, so with the aim of consolidation of the design. We have performed some vibration tests, this one in particular, by using the shaker that we have at Chile. And we have instrumented the test article with several accelerometers along the test article. Here are the results in terms of acceleration level. And again, in this case, the main results was that the kinematic functionality of the body flap assembly was maintained. And finally, we have performed a thermomechanical test, thermomechanical test on this component, on the outer flap support. The outer flap, one end of the outer flap was connected to a CNC fixture here through a beading interface, and the other end was connected to a metallic fixture. The test article was then put in a furnace. Here you can see the digital image here and the real image here. And test was performed by using an MTS machine. And we have used also 4 thermocouples to measure temperature. In particular, the most important one was the temperature close to the beading. The aim of this thermomechanical test was to verify the ability of the body flap to sustain simultaneously the design temperature and the design mechanical loads for a specific duration time. So you can see here the temperature, which is in the red curve as function of the time, and the target temperature, so the target thermal loads, and the target mechanical loads in terms of kilonewton. These target curve are divided in 3 phases. The most critical one is the phase 2, where the maximum load is about 12 kilonewton, and the maximum temperature is about 600 degrees. So these are the results of the test. Is a problem, maybe? Whatever. I'm sorry, the graph is missing here with the results. However, we can conclude that such maximum temperature was reached by the test, and also the maximum load was reached by the test. So requirements of the test were fulfilled, and post-test inspection highlighted that the test article have no visible damage. The thermomechanical test was repeated again 6 times for reusability proof capability. And as conclusion, we have used additive manufacturing to produce metallic attachment of the Space Rider body flap assembly. We have used a beading block approach to qualify the additive manufacturing parts. And we have performed some tests on the prototype level, so static, dynamic, and thermomechanical tests to prove the capability of the body flap assembly to be reused for the Space Rider mission. So let me to conclude with a picture of the thermomechanical test, and thank you for your attention.